let's get started. So welcome everyone to lecture 21 of CS 545, Introduction to Robotics. So today we are covering task-based region. It's a bit of an unusual lecture. It's less studied. It's not as much of a fundamental topic as other parts of the class because it's part of the research paper, but it's also part of what's in lab 4. So it's probably worth going through it in class a little bit. So I'll be having I do have my iPad, but it doesn't have the Google Doc with questions because number one, people haven't been using it. After the first few lectures, people seem to stop using it. And number two, I have the paper over here so that I can refer to it and some of my notes here. Yeah, so if you have questions, just raise your hand or just ask me after class. All right. Some logistics, so homework 3 is due, I believe, today. You may have late days left, and you can use it if you want. If you don't, then please submit it by tonight. Lab 3 is due April 12th. So again, look at Piazza for the sign-up details about how to use the robot in person. And we have also released Lab 4. So normally we would finish Lab 3 and then release Lab 4, but we got delayed a little bit. So we're releasing Lab 4 early so that if you're waiting on all the simulation or the physical experiment for Lab 3, you can get started with Lab 4. And yeah, we are working on homework 4, so we will try to get that ready. And then, of course, a couple of weeks later, we have the final exam. So yeah, looking forward to that. Any questions about the logistics? Yeah.
What's the exact time for the practice? The first of May?
I believe the final exam is on the 1st of May. It's on the course website, so whatever there should be the final exam time. I just went and looked at the times that were assigned to the classes that were Monday, Wednesday, 4 o'clock, and then they're assigned, I think, to a specific time. So it's out of my control.
Yeah, as I'm not in my flight ticket, so I'm sure everything finished before I get away.
So you booked your flight on the same day of the final exam?
No, 6th.
May 6th?
Yeah.
Oh, I think the final exam is in like May 1st. Have you seen the course website? The last line should be where the final exam, when the final exam is.
Yeah. I do see the website. That I was concerned about the time may change just a few weeks before the exam. So I want to be sure that the case.
Oh, you're worried that the time for the final might change?
Yeah.
If it changes, let me know. I've not been told otherwise, so yeah. Yeah, and these days most airlines, if you ask for a refund, you get a credit so that you can use it for you can use the same money unless you book non-refundable. Then sorry. Also depends on what airline you book. All right, other question. And by the way, I'll try to make sure that the last lecture there will be or at least the last week there will be final exam review, just like we had for the midterm. So. All right, so today we're talking about task-based regions. So before we get to that, we should probably review some of the relevant material that we've covered in prior lectures, some of which were a long time ago. So if you remember, we talked about transformation, right? And so a transformation consists of a rotation and a translation or a position. So here we're just showing the rotation part. And you can see that a rotation, you can represent it with a rotation matrix. Now, there are other rotation representations that have advantages and disadvantages, but rotation matrices are a common rotation representation. Yeah, because they allow for matrix multiplication, which can make things very mathematically convenient. And so you see that this thing will specify how a rigid body is essentially rotated from with respect to some frame. And we call the set of rotation matrices as the, remember what this stands for? Yeah, special orthogonal. Yeah. And then when we put those together in a transformation, we will typically use a 4x4 matrix with homogeneous coordinates. So remember again that the zero here is actually 3 zeros. It's like one row and 3 columns of zeros. And then this is how you combine rotation and a position in one matrix. Yeah. And then that will help specify an offset. Yeah. And more generally, you can have these be up to n dimensions. So like n doesn't have to be 3, but in practice, it's usually 3. If not, it's sometimes 2, for the sake of explaining things on like a flat presentation. So yeah, hopefully this is all a review. We have also covered sampling-based motion planning, right? So if you remember, we covered both probabilistic roadmaps and rapidly exploring random trees. So remember that for a probabilistic roadmap, this method involves 2 main steps. So first, you build a roadmap. So you have a bunch of different nodes where each node is a configuration of a robot. Again, if you want to think of it as a planar robot operating in 2D, so the configuration space is just specified with 2 numbers, then that makes it easier to think about. But in general, it could be arbitrary dimension. And then the roadmap would involve connecting, using a small local motion planner, any node that can be connected from one to another without any collision. And then you connect them, and then anytime you have a query, just run your standard like graph search algorithm to go from the starting node to the ending node, where you also have to connect the initial joint angle or configuration along with the final configuration to the roadmap. Yeah. And remember that probabilistic roadmaps were good for what? Single or multi-query? Single query means you just have like one query. Multiple query means you have to do many different queries of like, can you find a path from start to finish? So what are PRMs designed for? Multiple choice question, 50% chance if you get it right. Designed for multiple queries, you can use it for single query, but if you're going to use just one query, you might as well use the RT algorithm, because that will just stop when you find your path, and it doesn't bother building a more complete or potentially very complex roadmap. So you remember how the RT algorithm worked? So no, I even showed the video from the person who invented the algorithm, and you can find the link to that on the slide. So he just showed how to connect different nodes and then how it explored, how it densely covers the full configuration space instead of getting stuck in like a random a random ball like near the start. So remember that we started with some tree, and then you have a randomly chosen free configuration, which might be that black dot to the lower right. And then you have to find Q near, which is the closest neighbor of Q in the tree, which would be the red node. And then you try to progress it by some step size along the line from, Q near to, Q rand. Yeah. And then this is how you add a new edge to the tree. So remember that you don't add, well, you don't add this node unless you decide to continue to add it to keep expanding in that direction. You add just this edge over here. And we saw that this helped the RT algorithm like densely cover the space because you can randomly sample different points that are very far from it, and then you just try to expand the tree towards it. Yeah. Now for today, the point of discussion is based on task-based region. So this is a concept from this research paper from Dimitri Sirota and James, who were at Carnegie Mellon at the time. Like I think none of them are still there anymore. So the first author is now a faculty at Michigan. The second author moved to University of Washington. So, and the third one, I honestly forgot what he's doing, but I know he's doing some really good stuff. He helped coin the term cloud robotics, where you have, it's like you have a cloud, then you can call robots at a service whenever you need them, which is a pretty cool concept. So task-based region, they're a type of representation that's useful for planning paths, and specifically those with end effector pose constraints. So that's often the case in robot manipulation because if a robot has to manipulate things, usually its end effector has to be like within a range of acceptable poses. Yeah. I mean, if you're trying to grasp something, you wouldn't have the pose be super far away from the object that you're trying to grasp, for example. And task-based region is supposed to help represent constraints in this framework. So if you look at this example, and these were what simulators looked like back in the 2010s and 2009 and so. So you had your robot, and then there's some maze, and then what's the objective? The robot has some, I guess, some kind of pen, and then it tries to draw from, or at least it tries to go from a start to some kind of ending pose, right? Whereas where the the tip of whatever it's holding has to make contact with the flat surface. And for a task where the objective is just to go from your start to the ending point, there's specific constraints imposed by the environment. So some constraints might be, well, if we want the tip of whatever it's holding to remain like vertical and to be touching the table, then the height of the gripper has to remain constant. And of course, it can't exceed some bounds. And we might also assume that it can't like rotate arbitrarily, although you might allow some types of rotation among some axes. So, and I guess the bigger point here is that, and maybe a bigger takeaway overall, is that there's very often a set of infinitely many acceptable poses. And so if the robot is trying to grasp something, it can often be a little bit off, where it can often still grasp whatever it's supposed to grasp, but where we might change its rotation a little bit or change its position a little bit. And because it can do that to an arbitrary extent, then it can result in many different acceptable poses. So it's not the case that we need the end effector to be in a specific exact pose. So I think that's one of the reasons why people like to use task-based region for the flexibility that they impose in describing where the end effector can be located. And here's some other examples of different robots. So at that time, I think these were urban HRP3 robots. So, I don't use these robots. I don't know if people use them today, but they were probably a big thing back in 2009, 2010, and so on. And you can see that the robot is trying to grasp. Uh, this looks like a Diet Coke can, maybe. This one looks like a dumbbell, and this one is a kettle, like the thing you use to boil water, and then this one is just like lifting a pot. And the grip proposes need to be in some kind of acceptable orientation for a successful graph. All right. So here's some of the notation that we'll use today and also in the paper. So you have QBD, robot configuration space. So we've been using that notation earlier. So Q it shouldn't be new. It's just some space of some configuration space for robot, right? So if the robot has, if it's a planar robot and then it just moves in 2 dimensions, then you might have it just be 2-dimensional. Right? Now a path in the configuration space is tau. So tau maps from an input which varies from 0 to 1, and then it goes straight to an element in a configuration space. So it ranges from 0 to 1 because, if you have it longer, you can always just divide it by the time step and then get back to 0, 1. So now the new thing here that you have CQ be a constraint evaluation function, where you have CQ is a real valued function where Q is some configuration of the robot. And a constraint is defined as a pair of 2 things, where the first, well, where the S here is a subset of 0 to 1, although usually you'll see that it tends to be either the full 0, 1 or just the 1 at the end. We'll see what that means a little bit, but it represents the domain of the constraint. So where in the path is it active? So you have some constraint that the environment put on where the end effector can be located. So if F is the full 0, 1, then it's active for the full path. Yeah. So CQ determines whether a constraint is met at a given Q. And well, I got so this should be a continuation of the last bullet point. So met at a given Q and a constraint is satisfied when this is equal to 0 for all the configuration that happen to be in tau, where we only consider the part of the path where that constraint is active. So it's a lot of formalism just because for a framework you have to have some formalism, and then when you actually implement it, you'll assign some value to what these mean. All right, questions so far? Yeah.
Please explain the constraint again.
Oh, the constraint. So I feel like the constraints are going to be easier when we give some examples later. So I don't think that we're actually going to show some concrete instantiation of what the function C is like, but we'll show examples of like, here's a surface where the robot must be at. And then this is the constraint. So I think what happens is people convert that to like mathematical function, but I think for today, we're just going to look at different constraints at a high level, like with visualization of what they actually mean. Yeah. So we'll see some examples later. Yeah. Yeah.
And why the letter S should be from 0 to 1?
Oh, this. So the constraint might be active for the full path of the robot, in which case it must range from 0 to 1, but it might only be active for a subset of the path. So in which case you might have that F interval be maybe 0 to 1/2. Or if you only want it to be a constraint for the final pose of the end effector, you just make it equal to 1. Just 1 without the 0 up to 1 thing. So that's only if you want a constraint on the very last time step. Which very often we do, because if we want the robot to grasp something, often, that's the constraint that we want at the last time step, like to actually be in a position to grasp. Yeah, basically. And then the other bit of terminology to know here is that we are considering manifolds here. So whenever you see manifold, you should be thinking of something that is defined as a set where it consists of this thing subject to this other criteria, right? And then in this context, a manifold is a set of configurations. So that's what the brackets mean. So you have a set of configuration such that the constraint is equal to 0. And then you can repeat this for different constraints just by putting in this subscript. Yeah. And then the constrained motion planning problem is to find some kind of path, tau. So tau specifies, it has input, between 0 and 1, and then it maps it to a robot configuration. So you must have tau such that all of the cues that so I think the way to read this is a little bit tricky, I think. So here's how I would try to do it. I would say for all of the constraints, so you have I can be in 1 to n, all right? So I denotes the constraint index. For all the possible constraints, you have some kind of interval f, which is within some range of 0 to 1. It's going to result in this active portion of the path. Maybe it might be the whole thing, maybe it's just the last time step, or the first time step. Now, for all of the configurations that happen to be in the resulting path during the time the constraint is active, you have it inside the manifold. Yeah. So you see, I just read through it backwards. So yeah. Yeah. Did that make sense? Yeah. Okay. Yeah. All right, here's an example. You have a 3-link manipulator. So remember that we were talking a lot about different manipulator with different amount of links that had revolution. And then this is one example where you have some origin here, and then one link here, and another link here. So there's 3 links. And then you see here that there are 3 revolute joints. And so we're going to assume that that's the 3-dimensional configuration space. So that's why we can then plot it with a 3D plot. Yeah. And so you might decide, well, the example the paper gives is that the end effector must be on the line, so must be on this line with an orientation within plus or minus 0.7 radians of downward. Yeah. So the end effector can point down, and then that's 0 radian, and then it can tilt up to plus or minus 7.7 radian in either direction. Yeah. So And what this figure is showing is the set is the manifold induced by this constraint. So this is what happens if you try to visualize and show how the acceptable constraints can be mapped into the 3D space. And so you look at the shaded region, each point in there corresponds to some configuration of the robot such that if the end effector is touching a line and it's pointing down with the appropriate range of angles. I don't actually know how they got that, but this is just how we this is just how to think of the manifold. Yeah. All right. Now, if you look at the prior slide, you'll see that this manifold it looks like it's a very small subset of the range of possible configurations of the robot. And so that leads to the next question of how do you actually sample within how do you actually sample a configuration within that manifold? And we might want to do that because, well, I mean, we might want to sample a robot pose, and then we ideally want it to satisfy all of our constraints. All right, rejection sampling. I think this is the most naive one. So this corresponds to the one that's to the far left in their figure. So simply generate sample Q, check if CQ equals 0. Is that good? What's the problem with this method? Yeah, well, yeah. So another way to put it is that if your constraint manifold is, especially if it's of a lower dimension, then the probability of a naive sampling, if you just try to sample everywhere in the high dimensional space, so one example is you have a sphere, and then if you're trying to, if the constraint manifold is such that it's only, if this is only equal to 0 when you sample a point that is in a plane that is within a sphere, then when you randomly sample, the probability of getting on that manifold, it might actually be 0 depending on your interpretation of the measure theory involved. But if it occupies a large dimension of a large amount of the of the normal configuration space, then it's probably okay. So, and it's also very simple. Sometimes simple is easy if you're like talking to lawyers and stuff. So, all right, the second one is projection sampling. So what happens there? You sample different poses or robot configuration that might be like arbitrarily located in the set of possible configuration. And then you run a projection strategy to map them to the closest configuration that satisfy the constraint, which means the closest point on a constraint manifold. Yeah. Of course, you have to be able to determine like what is the projection strategy. That might be complicated. So, yeah. But at least just think of this as a visualization. This example here is showing there are two manifolds. One is over here, which is the two-dimensional blob. This other one is a line segment, which could be a constraint manifold. And the third way of sampling is the direct sampling method. So I think the way to think about this is you need to be able to parameterize, or you would have to be able to define some kind of mapping between any point on the manifold here with any point in some kind of function that is a little bit easier for you to specify a sample from. Like this might be at least the example they're using here is based on a 2D grid, which you can easily sample from. You can sample X coordinate, Y coordinate, and then presumably there's some kind of function that or parameterization that maps it to an element in the constraint manifold. So this thing here can be pretty tricky because then you also have to figure out how do you define that mapping, which might not be easy. So I think later in the lecture, we'll talk more about the second one, the projection sampling. So, hi, task-based regions. So task-based regions are a specific constraint representation, so mentioned earlier. Now, what they more specifically do is they describe n-vector constraint as subset of the special Euclidean group in 3 dimensions. That's what this notation means. And so the pose of a manipulator's n-vector is a point in that special Euclidean group. And it's mainly meant to be used in a sampling-based motion planner. So we were talking about those earlier, like the probabilistic roadmap or rapidly exploring random tree or many different variants. So you remember bidirectional RT and many other variants. Yeah. So I got the main, again, I kind of mentioned this earlier, but the main thing is it's designed to present constraint, but without specifying that the pose of the end effector has to be in this exact position and orientation, because that would be very restrictive. So. And the application are, how do you grasp an object and then how to manipulate an object with constraint. So. All right. So it consists, all right, so more formally, a task-based region consists of 3 parts. Now, the first thing is it's a little bit frustrating, but the notation that they use here is a different type of, it's an equally valid notation, but it's different from what I used in, I think it was lecture 14 when we talked about transformation. So if you remember that we talked about TAB, right? But now they're putting it as T with the superscript of A with with a subscript of B, right? So let me just write out what the equivalent is. Do you remember that when I talked about the yeah, so you remember what this means, by the way? Like, what is TAB here? In the notation that I was using before. It's written on the slide. All right, pose of B and the coordinates of A. But you see what this is the same thing as that. And by the way, to make matters worse, sometimes you don't see it here, but there might be other textbooks or resources that use notation like TBA, like that with the reference frame over here. So just be mindful of this notation. So, yeah. So I'm mainly trying to keep as much of the notation from this paper as possible, but it is just be aware that they use it's the same conceptual thing that we were talking about, but just a different way of like writing out the math. So. All right. So TBA is the pose of B in the coordinates of A. So just think of it like you have A here, and then there's B here, and then like if this is the X direction, then that transformation is going to be like in the positive X direction. So if this were reversed, then the X would be negative. Just as an example. So there's a couple of main, so the three main parts are over here. So the first one is a transform from the origin to the task space region frame W. So usually W refers to like some object of interest that the robot is trying to grasp. So just think of W as like being centered at that object, and then the origin, which is the 0 here, that is like the world pose. So don't get confused with again with the W and world. That's not what W means here. So W here represents the TSR frame, and then 0, or I guess that's a 0 here. So the 0 represents the origin. Yeah, so it's a little bit tricky because sometimes I call it world coordinate as the same thing as the origin, but it's not here. So yeah. All right, everyone clear on the first thing? What about the second one? So this is the pose of E in the coordinates of W. So the pose of E, so E is the robot end effector. So maybe let's use an example. So this is the object to grasp. And so W is going to be centered at this, University of Toronto mug. And then the robot end effector is E. So E is going to be centered over here, like right where the end effector is. And so this distance and the rotation is TEW. Yeah. And then BW here is the 6x2 matrix bound in the coordinates of W. And so they use different bound in the XYZ axis. And for the first three, and then the last three are bound in the rotation using the roll pitch yaw convention. Right. Why do they use roll pitch yaw? Well, because it's easier to think about specifying constraints in those, even though the roll pitch yaw rotation convention has a lot of weaknesses compared to quaternion, but for quaternion, it's harder for us to think about what is a good bound on the ranges. I actually don't know. So yeah, we covered quaternion a little bit earlier when we talked about rotation and representation. I'll try to cover it more in the advanced topic because we cannot do a robotic course without talking about quaternion in detail. All right. Any questions on that? Yeah. You're explain what thing? Oh, the roll pitch yaw convention. So I think I'm gonna show some examples later, but you can think of roll pitch yaw as corresponding to the Euler angle. So if you have like X. So roll, depending on your convention, if you have roll pitch yaw, then each of those three are going to correspond to one of these axes. And so you have some rotation about this axis, some rotation about this axis, and then some about this axis. Now, by default, you can think of them as like having zero rotation, but the bound might be like, it can only rotate from minus pi over 2 to pi over 2 in one of these directions. Yeah. What about if I said it can rotate from minus pi to pi? Then there's no real bound, right? Like it can rotate like basically anywhere in the anywhere it can. In that specific axis. Hi, end effector offset. So remember that I mentioned that the task space region frame is W, not W is not the world or the origin, it's the task space region frame. And the end effector frame is E, so that one's a little bit at least easier to remember. So usually W is centered at the origin of an object held by something. But I guess I shouldn't say hand here, it's like gripper. No. Or some location useful for grasping, like the handle of a cup. So if we look at this example, I guess for this soda can, you have W, which is like, it's centered somewhere near the center of that can, because that's the thing that the robot is trying to grasp. And then you see that the E is centered at this end effector. So the end effector is like, well, this is another side comment, but when people talk about end effector poses in robotics, they're not usually talking about the tip of the fingertip. They're usually talking about the thing like the wrist right before that. And so fingertips are often different, they're gripper dependent based on what you decide to drill or screw on them, but the end effector pose is usually like this wrist thing that is just before the fingertip. Yeah. And you can see some more examples here. So if the robot is trying to grasp the cup just by gripping, by moving downward and then grasping, then the W would be centered maybe somewhere by the center of the cup. So it actually doesn't coincide with any part of the cup. Like the origin does not coincide with the cup. But if it's over here, like if the robot is trying to grasp by a handle, then you would make W be coincident with the handle. Right. And then the end effector is going to be like some offset before that, which is what this is. So that's why TEW, I guess TWE if I'm trying to be consistent with the prior notation. So TWE is part of the task space region. So, okay, yeah, this is just hopefully one example of how to visualize the W's and the E's that you'll see here. All right, questions on that? All right. All right, so let's talk a little bit about this and then we'll take a short break. So, all right, so here's another like example. So again, using this is a simulated robot, and then it's trying to grasp this can. And then it has, all right, so there's a couple of things here. So the first thing is this thing. So this is your like origin. So it's like the reference of like the base frame, or whatever word you want to call it. Now, W is defined here. Then E is over here. So E is like that end effector pose that we want the robot to get. But of course, the robot is over here, so it's not like actually in the unacceptable pose. And so the objective is, well, how do you plan to reach to that? And then you can use task space region to determine like if to determine an unacceptable robot gripper pose, then you run some planner to get there. Yeah. So again, I think we covered what these three mean in the prior slide, right? Yeah. So T0W, TWE, and then we have, yeah, T0W, TWE. So I'm going to try to say the superscript first, and then the subscript, because then it'll be like consistent with the prior notation we were using. All right, and then there's a whole bunch of other frames here. And depending on how close you are to the screen, you might see that there are arrows that point from one frame to another. It's a little bit hard to see. If you're reading the paper, you might want to zoom in a little bit and then see the direction the arrows are pointing at. So for example, you have an arrow that points from this frame to the W. And so that is T0W. So the way to interpret that is it's basically showing that, yeah, the transform to the TSR frame W, like it's indicating in the coordinate frame of here, in this coordinate frame, what is the position and rotation of W, basically. So like if this represents the y-axis, because I think this is red, right? The x, I think it's red is x, and then this is y. So if because of this, then the T0W would probably have a positive y value because it's pointing straight in that direction, and then the z and the x might be close to zero because it looks like it's very close. Well, the z would be a little bit positive because it's going up a little bit. And so the way that I like to think of this is you have some frame that that point the arrow points from one to another, and then that's how you can also tell which ordering it should be. Is it going to be T0W or TW0? Yeah. So I think it's T0W, which represents the fact that zero is the reference frame, and then it's expressed within that frame. So. All right, let's take up a 5-minute break, and then you can just look at this figure if you're going to stay here. So, um, yeah, we'll be back at 4:50, 4:54. You have a question?
No, we're still at the wall.
You have 3 minutes. Okay, there you go. Hard to see the arrow. Like, all right, let's get started. All right, so let's take a look at some examples of specifically of the matrix of bounds. So we talked about B here. So B is that 6 rows by 2-column matrix that represents the bound. So it's like the first 3 rows represent the positional bound, and then the last 3 are the rotational bound. And again, they use the roll pitch yaw convention. So this is a figure from, I believe, the paper where they describe the types of bound. And again, the main reason why they use the roll pitch yaw is that it's intuitive for a human to specify the limit of how much something should be allowed to rotate along one axis. As a general principle, the Euler angle notations are a bad rotation representation, but we'll just use it here because it's intuitive to describe. But if you're a professional roboticist, please be aware of the shortcomings of Euler angle. Yeah. All right, here's an example. So let's say that the constraint should be imposed that the robot end effector should always touch the table. So I guess imagine that imagine that the object that the robot is holding should always touch the table, but that there can also be some rotation about the point when that thing makes contact. So it's allowed to pivot up to plus or minus alpha radian while it's making contact. And because we haven't specified things like positional bound, you can make the x and y be like minus infinity to positive infinity, but you can also make it be like minus x plus x if you know like how far it can go in some direction. And then why is this 0? Third row. Yeah, so the pen must exactly, the height of the pen must not change. So this is an example of how you might specify things. So the reason for minus alpha and alpha just by some assumption, like, you have a pen and then we're allowed to pivot in some direction. And then, yeah, so I guess it's like you're allowed to pivot, but not like to actually lift the pen. Yeah. But the reason for minus alpha and minus pi and positive pi for the yacht here, because you can have the gripper be like anywhere in it can rotate, it doesn't have any constraint in there. I mean, in practice, you might also impose a constraint, but this is just an example. It's not meant like you can easily come to me and say, well, this is you should make this matrix of bound something different, right? And then if your argument makes sense, then we should do that. So this is just an example of a matrix bound. Right. Hi, here's another task or another example. So yeah, this one another from a video here. So this is a really old video. So the first and third authors are now like graduating PhD students. They were undergrad at this time, very good one. And then they were at Carnegie Mellon where they had this robot, and then there were a robot. The robot had to stack 3 cups. And yeah, so there's 3 cups, robot has to grasp and then stack them. Yeah, that's what simulators were like back then. Yeah, you put the cup there, then the object disappears. Yeah, so anyone who's used more modern simulators, you can kind of see how the physics simulation has improved since the time of like 2009 or so. That's a very different era in the world. So can someone explain to me, like, why might this be the matrix of bound? This thing here. Yeah. Yeah, the cup will drop anyway, and then we assume that it's gonna perfectly drop. Sure, yeah. What about the angle here? Wait, did you mention the angle? Oh, you only talked about the position. What about the angle? Like, So remember the last slide, we had minus alpha and alpha here, but here we're having 0 and 0. Yeah, because before we allowed some amount that we could pivot in the non-yaw direction, which would be the roll and the pitch here. But if you do that, then you effectively you have 2 cups, but then that would be like rotating one this way. But you're allowed to rotate this way, because if you're just rotating this way, no, the cup is symmetric about the z-axis, and so it's going to be fine. That's why you have minus pi and pi. Yeah. Again, so one way to think about this is that the TSR frame is going to have to be centered like somewhere at the center of the cup for us to justify why the first 2 rows should be both 0. Yeah, but then it assumes that there's no wiggle room that you can have. I mean, again, in practice, you might argue, well, maybe we should have a little bit, in which case you should change your BW matrix. So. Hi, another matrix of bound example. So this was a very interesting example that they had in the paper, like a robot that was handling a dumbbell. You've used those before, right? For like weightlifting. So I don't know how many weightlifters there are, but this is like what weightlifters use. Like there's dumbbells, and then the robot is trying to hold, I guess hold the thing here. And what they did here, they assumed that there's going to exist some sliding surfaces that can help partially support the dumbbell. So if you look at this and that and this, those are surfaces that the robot can use to help support the dumbbell. Like if it's putting it on this surface, it can hold the dumbbell and then use it to slide in that direction. Yeah, they actually have some videos of their robot actually handling the dumbbell, although it's with like straight, like non-slanted surfaces. But in theory, you could have slanted surfaces. And you can define pose constraint task space region at the center of each sliding surface. Yeah. So what would that mean? So if you look at this one, you have TW10. Or sorry, it's T0W1. Yeah, I should say the subscript, the superscript first, right? Yeah. So this is T0W1. So with respect to the origin, it tells us the transform needed to get to that, well, at least the coordinate with respect to the origin frame. So why did it have BW here? Well, if you have your slanted surface and the dumbbell is on it making contact, then the z-axis point in a tilted direction. Yeah. Right. Yeah. So the z-axis points in a tilted direction. So you can rotate about the z-axis however you want, but you still cannot pivot, because then that would change the dumbbell so that it's not like its end edge is not completely touching the surface. So that's why you still have, that's why we have 0, 0, 0, 0, minus pi, pi. Yeah. Because if you pivot, the edge is going to lose contact with the surface. So again, this all assumes that the point of this is to make sure that the dumbbell is making complete contact with the sliding surface. And it's minus L over 2 and L over 2, and then minus W over 2 and also minus W over, oh, this one is probably a typo. It should be like W over 2. So it can be like anywhere on the surface of, the size of, the surface. It can be anywhere along the surface of that, that planted region, I guess. Then alpha here, so you can, I think what the paper does is they might actually put 0 here, but you can also put in an alpha here. It depends on if you define your E here to be like the actual tip of that weight or somewhere near the center. But either way, the height is gonna have to stay the same. So yeah. So any questions on this example? I can change it to be like W/2. Yeah. Yeah, it is. Yeah, it's W/2. Yeah, yeah. All right, transformation to world coordinate system. So, and this one, I actually have to say that there's one part here that I think there's a minor, like, there's some kind of typo or misunderstanding here, but I'll explain like how my interpretation of how their figure works. So what this is describing is a way to try to sample from anywhere in the bound. So remember we had the matrix of bound that's, if we sample within those, we should be sampling a pose, right? And then the objective here is convert that 6-dimensional thing to a pose, a transformation with respect to the origin or the world coordinate system. But again, the world coordinate system is origin, not W. So again, just keep that in mind. Everyone okay with the problem statement? So if you sample F from BW, you can do a uniform random sample for each of the 6 components. And then you get some value for each of the 6. And then you convert the 6D vector to a transformation in the special Euclidean group in 3 dimensions. How do you do that? Well, the way I normally do it is I just call some code that does it for me. So there, you can convert like yaw, pitch, and roll to be in a like rotation matrix format. So I think the advice that I have is look at the code that you use to convert from those 3 angles to a rotation matrix and check the ordering of the yaw, pitch, and roll stuff. And then what is TWS here? Well, that would be, so you have the S over here, then you have W, which is over here. And so think of it as something that is centered at W, but it's describing the position and orientation of S, where the coordinate frame is measured with respect to W. Yeah. Now, the sampling step here involved a conversion from the object to the world coordinate system. And here we use the subscript cancellation rule. So you remember how this works? Let me give you an example. So this is where their notation, the notation that I was using earlier was T0. Yeah, this was the notation I was using earlier. And then if the second subscript of the first transformation matches the first subscript of the second one, you can cancel them. And then that's what happens when you do your matrix multiplication. I mean, I greatly prefer this notation, but just be aware that many sources will use this notation. And again, sometimes they'll move this thing to the back. And then the last step is what the paper called applying the end effector offset transform. Now, this is the part where I think that there is some kind of really bad typo with the paper, or there's some other misunderstanding that I have. So I think what this is trying to show is it's trying to show how do you get this thing here. This is visualized as, you have your your sample prime, which is over here. And then you're trying to express it, like describe the position and orientation, where it's assumed that it's going to be in this coordinate frame of the origin. Now, the way to think of this, in the way that I have been thinking of this is, you can go from like 0 to W here. Like if you go from 0 to W here, that's where this arrow is pointing. And that's where you get T0W. And then you have TWF, which is this transform. So it's sort of like you have another arrow from W to S here. Well, then they also have TWE, which is pointing from W to E. And to me, that doesn't make any sense. I think you're supposed to go from the inverse, which is going from F to F to prime, because this is the inverse here. So in my opinion, the offset transform, it probably should be inverted, but the paper had it non-inverted. So I'm not sure where the error is somewhere. So if you're working with this, just try both ways and then visualize which one is actually working. Yeah, sorry, I couldn't be much more helpful than that. Yeah. But I'm hoping that at least the way to think about the arrows and the subscript cancellation rule, like that at least should be okay. So and then the point of all this is you get your transformation of that sample, and then you run inverse kinematic. And then what does the inverse kinematic do? It tells you we know the desired pose, and we want what are the joint angles of the robot that will lead to that. That's the whole point of doing that. Like the robot has to go somewhere. So, yeah. All right. So remember earlier that we also talked about building a constrained path, right? So we had projection sampling, which was the middle part here, where we sampled a bunch of poses or configuration. And then we want to be able to project it to be close to the manifold, right? So the way that we can do this is by using some form of gradient descent. So here's how it's going to work. So we have some kind of configuration Q. And then it can be arbitrary. And then we have to map that to the closest configuration in that task space region. Right. Now there's three main algebraic steps that we have to do here. So let's just go through them. Yeah. And by the way, the thing that we're actually trying to find, know what this means. So it is TWF prime, which means it is the samples like I guess the offset point which represents the offset point from the end effector, the current end effector. And then this transform is trying to show its value in the coordinates of W, which is like the desired area, that is the task-based region frame. And then that transform is like describing the, in some sense, distance, like how much you have to translate and then rotate in order to get to the current gripper position, which is not in the task phase region, so therefore we have to move it towards that. So that's where the dw here means here. So TWS prime I'm just gonna invert it to change the ordering because it's already complicated enough here. So let's just simplify it. So TW0 F will be and then you get subscript cancellation rule, right? So if the all right. This is the simplified version. Now, the way to think about this is if you look at the prior figure, T S prime W is this thing here, right? Yeah. So it's showing this is the transform from here to here, right? Yeah. And then presumably, like if we know that transform, then we could just try to like undo that in some sense to get the robot gripper to be in the right spot. Yeah. And so you can think of this like if we go back to the original equation here, this thing is equal to TW0, which is this. No, this oh, so it is T0W, which is must be here to here. Yeah, yeah. Here to here, and then T0F, so it goes here to here, up to here. And then you get your this thing here, which brings you to here, right? And so this is how I think of it. So these three terms brought us from here to here to here and then to here. And then we have our T of prime W, which is like from here to here. So yeah, so I at least that's where my intuition at least matches what the formula is. Yeah. And hopefully the first sub-bullet point, I hope is a little bit clear, like given your configuration, you can use forward kinematic to get the position, or really that should be the pose, including the rotation of the end effector at this Q in the world coordinate. And so this was your end effector here. And then, yeah, with respect to the world coordinate. And you can usually just run forward kinematics in like any off-the-shelf like robot code. Yeah. And then, yeah, you apply the inverse offset to get the pose of the object in the world coordinate. And then, yeah, I guess you convert the pose from the world coordinates to the coordinates of W using this. So we talked about this. So like that's essentially turning it from the world coordinate to the world coordinate to the object coordinate. Yeah. Because again, W is not the world coordinates here. Like one of my biggest pet peeve about the notation here. Yeah. All right, is everyone clear up to that point? I mean, if you are, that I'm pretty impressed. Like, I find it to be a little bit confusing at first to go through all the transforms. So what is DW here? So remember that DW is the 60 vector that corresponds to this thing here. Like visually, again, it is this thing here. Like it's how much, like it goes from your desired TSR up to like where is that where it's actually at. So it tells you like how much you have to change to go from where the robot is to the actual target. And then if what is showing here is the translation. It's the translation vector, and then these formulas come from like converting a rotation matrix to roll pitch yaw. Yeah, if you're confused, look up the formula for how to convert from rotation matrix to roll pitch yaw. Yeah. And then finally we have delta xi. So delta xi is like some kind of change that we can make to the uh, like it specifies how much we would have to change the pose in order to like better satisfy the constraints imposed by our BW matrix. And so what is showing is that for all of I here, if the component of DW here satisfies the constraint, which is the third one here, you don't have to change it. But if it is below, this, then you have to sort of like you would have to increase this, and then if it's greater than, this is also another change that you have to make. There might be another typo here, actually. There's hold on. Oh no, it is good. Yeah. Yeah. Oh, okay. Yeah. So just think of this as like some kind of change that you have to make in order to better satisfy the matrix bound. Yeah. All right. So here's some high level. Now taking a step back from all the details here, here's some high level thoughts about how to plan with task-based region, right? So task-based region can sample goal end effector replacement of a manipulator where you can make a constraint be CQ is equal to distance to task-based region of Q. Yeah. So I think we covered distance to task-based region like in the last slide. So we talked about like the distance, to the task-based region. And if it's 0, then it satisfies the constraint. Then this last thing here is just 1. Like it's not 0 to 1, but that's because it only specifies the very last time step. So. And the procedure that you could do is you sample directly from the task-based region, get some kind of pose. And then the sampling here is based on like what we covered earlier, like you sample a pose, then you have to sort of project it into the acceptable region. And then you pass that pose to an IK solver to find like where are the joint angles, what are the joint angles such that they lead to the end effector being in the task-based region. And then you rank the solution, run RT with a small goal precision for the highest rank goal solution. Now you can also plan with code constraints based on the entire path. And this is another framework to try to plan with task-based regions. So you can plan with a constraint, like the same constraint as earlier in terms of the function CQ, but now we just make this be the entire interval from 0 to 1, because this constraint must be active for the whole path instead of just the end. Yeah. And then every time we run RT, then we project to the constrained manifold using the same projection thing that we had talked about. And then in the paper, if you look at the on it for more detail, you can see how they project using the Jacobian transpose method, which is also something that we covered a little bit in the inverse kinematics lecture, which I'm still trying to get a video for that. So just be patient until I can find the time to do another recording. Yeah. Yeah. Any question? All right, final thing for today is to talk about constrained bidirectional RRT. So what do you think it means? What do you think the name implies? So you have RRT, and then it says bidirectional. Do you remember what that bidirectional means? No, wrong direction. Yeah, bidirectional does not mean this way, it means this way. You start with two trees, and then you're trying to branch them so that they come closer, they have a path that connects them. Yeah. And then what does constrained mean? Well, constrained implies that you're probably going to grow the tree, but they're subject to constraint where the trees can grow. So hopefully the name constrained bidirectional RT makes a little bit of sense. Yeah, and it is a probabilistically complete algorithm. So remember how we talked about RT not being probabilistically complete, which is not something we want to see. So we ideally want it to be like it'll find a solution if you eventually run it long enough, or it'll find the optimal, like, yeah. Yeah, so try to grow two trees in the C space of the robot. So what happens here is there are two main cases. You have add root, and then you have the other things here. So the add root try to inject a goal configuration into the tree. So you try to include a goal configuration. If you can connect to it, then you're good. Because you've connected to the goal, or at least somewhere in the goal. And if you're trying to explore the C space of the robot, then you randomly sample a configuration, because that's what RT does. Like you randomly sample some configuration. So you have QRAND. You find the nearest neighbor. Again, that's standard in RT. Like you have your randomly sampled point. You find the nearest neighbor that is within the tree already, and then try to grow to it. What do you think constrained extend means? Why not extend? Why not just extend unconstrained? Well, first, what does constrained mean? Like you try to grow in some direction, but you're constrained, which means that you cannot grow in some direction. So basically. So it'll try to grow the tree towards QRAN. So constrained extend will have some tree, the current nearest neighbor, and then some target node. And then it'll try to grow towards it, but it'll stop due to a constraint. Visually, it might look like this, though. You have Q near here. So think of that constrained manifold as this blob thing, and then you have a bunch of node that show the tree already. So the tree is coincident with the constraint. And then you have the nearest neighbor. And then you try to grow the tree toward to target. But instead of growing towards it, you sort of project it back to the manifold. So that's that's a visualization of the constrained bidirectional RT. Did that visual help? Yeah. All right. So to summarize, we covered task space region, that some of it, hopefully it's good enough for lab 4, and yeah, good luck on that. And I'll see you on Wednesday then.